As we move on to the next chapter, we're dealing with the concept of probability. That's what chapter 11 is about. And in topic 1, we're going to look at some basic concepts and dealing a lot with vocabulary. So the language of probability. You go to the supermarket, you select 5 pounds of peaches at this much per pound. You can easily predict or know the amount you will be charged at the checkout counter. It'll just be 5 times this. This is an example of a deterministic phenomenon. That is, you can predict exactly based on the number of pounds and the cost per pound. Now, on the other hand, if you were the product manager, the fellow in charge of selling fruits and vegetables, you would like to know how many pounds of peaches you should order to see if you have enough for the expected clients. See, that's something you don't know for sure. This would be what is called a random phenomenon. And this fluctuates on any given day. On Mondays you can expect this many customers. On Tuesday, Wednesday, Thursday, Fridays a lot of people shop, Saturdays, Sundays. So you see, this is a challenge. Now, in this section and chapter, we'll be looking at the overall likelihood of events occurring. And this is probability. I'm not sure I mentioned, but my background when I taught high school was in biology. And we do study probability in the area of genetics, which they do mention here a little bit. And of course, in science, we're always doing observations, measurements of random phenomena. This is an experiment, so another key word. Now, the possible outcomes, the results, are outcomes, and then this is set over all the different kinds of outcomes that could take place. You're getting specific outcomes, but then there's a whole field of outcomes. This is called the sample space. So these are words that should be listed in your notes, and you can go back, of course, to the textbook and study them. Now, as we look at a collection of possible outcomes, as we see in this Venn diagram, that if the outcome we're looking for fits within what is called the favorable outcome or successes, they fit within the colored area. And then E represents, you might recall, the universe. That is the kinds of outcomes that we call the sample space that we're looking for. So we have some symbolism that we'll be looking at. P stands for probability. The probability of E out of the events of the sample space S, that we'll get a real formula in just a few moments. But how do you figure out your probability? Well, they're mentioning there's 2 ways. One is theoretically, that is just mathematically, and we'll show you examples of that shortly as well, or empirically, which means you are physically trying something and then that results through experimentation, give you a ratio of events. So let's look at this in more detail as we look at examples of probability. Now, the simplest thing is, as we see here, finding the probability when a coin is tossed. Now, on a coin you have two sides, the heads and the tails. So what are the kinds of events that could happen when you toss a coin? And you're going to say, well, there's two possible events. So your sample space is 2. Well, what event are you looking for? Well, you're looking for, let's say, a head. Well, that would be one possibility. Or you're looking for a tail. That is one possibility. So the likelihood or the probability when you toss a coin, and again we're assuming that this coin is an honest coin, it hasn't been set up in such a way that one would come out more frequently than the other, is 1 out of 2. That's the probability. Now, again, you've analyzed this and you've looked at it, and you might say, well, is there ever a possibility when you toss a coin that it's going to land on its edge and not fall down on a side? Well, the nature of a coin is such that it would be, really improbable for it to land that way. Now, as we look at example 2, they're giving us this styrofoam cup. If a styrofoam cup is tossed, find the probability it will land on its top. Well, this is the top here. This is the bottom. And interestingly, in this case, this is the side. So theoretically, there are 3 possibilities. It could land on the top, could land on the side, and it could land on the bottom, like this, in its upright position. And you might say, what's the probability? Well, you don't know. So what do? Well, you do some experimentation. That is, you toss the cup a number of times. And let's say if you toss it 50 times and it lands on its side 44 times, it lands on its top 5 times, or it lands on its bottom just once, then you have a way of starting to figure this out, because you have developed data, which is what we do in scientific experiments. We develop data that these are our observations, these are the results of our experiments. And we have gotten then, if it lands on its top 5 times, and again, you don't know exactly if it's always going to be doing that. That's not mathematically found. This is empirically found through trial and error, through collection of data, that you get 5 out of 50. So generally we reduce it to lowest terms. So your answer would be 1 out of 10. Your possible sample space was the number of times you conducted the experiment and the number of events that were favorable to what you're looking for, that it will land on its top is a ratio of that to its sample space. So example 1 with the coins, and again we mentioned they were fair or honest coins. They weren't weighted to give unlikely results or favorable results. This was figured out mathematically since there were two possibilities equally likely. Then we could figure out the ratio. That is their probability. This applies to dice rolling, to card games, to roulette. If they're honest games, and you don't have a card shark or something in there, or loaded decks or loaded dice, lotteries, if they're fair, all of this. And in 1812, a fella, I guess he was Laplace, developed this formula. So let's take a look at it. So again, we're dealing with probability, the P, of an event is the number of favorable outcomes, which is the number of E, which is favorable outcomes, divided by the total number of possible outcomes, that is S. So the event you're looking for over the sample space is a way of looking at it. This is a formula you should have in your notes for probability. Now this is theoretical probability, the kind that we can figure out mathematically. Now, when will I ever use this? This is interesting, and we should look it over. I could recall seeing in movies that I've watched, especially some of the old movies, where who's going to do this? Well, let's flip. And whoever has heads and call it and stuff like that. Now, I could remember as a child that, the older students would say, hey, do you want to gamble a little bit? And in those days it was a penny or maybe a nickel or something. It was a lot of money. And we'd say, oh yeah, a chance to win, and gamble. So we'd flip. And it seems that the older student always won. I couldn't figure that out too well at the time. But then what happens if you're just flipping, some students have developed a way of putting a coin on their thumbnail and then flipping it, and depending what they put on their thumbnail, if it was heads up, then they would always get a heads. If it was tails up, by just learning how to flip it, so it wasn't an honest random flip. They had developed a skill of flipping. Okay. So the thing is, you flip it and then let it land on the floor. That adds a little more honesty to it, as opposed to catching it and flipping it on your the back of your hand or something. Then you might say, can this be done for 3 players? Well, if each player has a coin and they're doing it honestly, well, 2 will have 1 heads or 2 will have tails, and 1 will have the opposite. Or if they're all the same, it's until the odd man wins, and it's described here. So again, and I don't know if you'd use this or not, but that might be a way. And they show the possibilities here. Now, looking at example 2 with the tossed cup, the likelihood of various outcomes was not intuitively clear. That we ended up with landing on its top 1 out of 10 times was based on 50 tosses or 50 throws. That may not be enough but it gave some kind of approximation of perhaps the true theoretical probability. So we found that experimentally, or as we say, empirically, resulting in our probability formula. So the empirical probability formula, as opposed to the theoretical based on mathematics, this was based on experimentation, is very similar. And often they put wavy lines here, but whatever. The number of times event occurred out of the number of times the experiment was performed. So very similar, but one mathematically derived, the other experimentally or empirically derived. Empirical is sort of like hands-on, and the other is in theory of what goes on. We often refer to the other as, in biology, as the hypothetical. Going on to example 3, we want to find the probability of having daughters. Well, Kathy wants to have exactly 2 daughters. Assume that boy and girl babies are equally likely. Find the probability of success for the following cases. She has a total of 2 children. Well, we often use the formula, and they're using a little bit different method of actually listing. But we would say the probability of getting a girl is 1 out of 2. I think you would agree to that. And then we would times that by the probability that the second would be a girl. So this gives us 1 out of 4. And that's what they get too. So listing them all in your sample space this way gives you the same results. Now, if she has a total of 3 children, that they're all going to be girls would be 1 out of 2 times 1 out of 2 times 1 out of 2 is 1 out of 8. And we see we will get that here shortly. Well, the way I figured it above is if it were at the same time. Here they're saying if you have 3 children, what's the probability of having 2 girls? And according to their tree diagram, that is also 3 out of 8. That you would have 2 girls and a boy. Now here, keep in mind that order is not important, and other things that we have mentioned in previous sections we will be talking about in our next section, probability of events, and some of this will come up there as well. So in looking this over, it says when you are dealing or drawing cards, as we'll be talking about, the dealing is generally done without replacement. So once you give a card out of a 52 card deck, if you give 3 cards out, you only have 49 cards left. So once dealt, a card is not replaced in the deck. So all cards in hand are distinct. Repetitions are not allowed. In many cases, such as building 3-digit numbers, changing a little here, repetitions of digits is allowed. For instance, 255, the 5s are repeated. This is a legitimate 3-digit number. So digits are done with replacement. And order is not important. So again, we're going to be using some of the stuff as we figure things from previous sections. Well, we worked on some of these in the last chapter. We're looking now at picking out from our data. We aren't expected to know all of these, but they're saying a full house out of the possible combinations. So there is the full house, and there is the total number of combinations, and we can simplify it to this, or we just want a decimal fraction anyway. We can see it's not very possible. The table shows that there are, let's see, a royal flush now. This would be 4, a royal flush. Again, I'm not familiar with cards out of this, and it's even less common. So again, I'm sure if you are a card player and you want to do it to make money and gamble, you have to be really super good. And I don't know the qualities for that, but it's not very likely. Some background. For examples 3 and 4, both utilize theoretical probability because we're assuming all possible outcomes were equally likely. Now, when we have example 3, the likelihood of a girl baby to a boy baby was assumed that they were equal. Generally, we have more male births, while male births occur a little more frequently. There usually are more females living at a given time due to higher infant mortality rates among males and longer female life expectancy in general. Okay, so these were some background things, and again, this really ties a lot into biology here. We would reflect on this as well. Okay, example 5 shows a way of incorporating such empirical information. So let's take a look at that. So here we're finding the probability of a gender, male or female, of a resident. And they give you some background that there was actually a census. Every 10 years there's a census, and it was estimated, because you may not have hit every single person, but you can get a general, this many males and this many females. If a person were selected randomly from a population that year, what is the probability that the person would be male? Well, your outcome that you're looking for is a male, so that would put the number of males there. Out of your sample space would be the sum of these two, and it comes out to be that as a decimal. Again, this is a little smaller than this, so this value is appropriate, that it's somewhat smaller. Now, in this section, we're dealing with the law of large numbers, or as you may have heard, the law of averages. What does that mean? Well, remember we were collecting data when we tossed the cup, and we did it 50 times. And we said it's going to land on its top 1 out of 10. But any one time that we toss the cup, it probably wouldn't land on its top. Why? Because the law of averages states that. We used to do a lab in our biology class when we were working with genetics to go into this a little bit, where we'd have these little cylinders, and this would be, let's say, a white cylinder, and this would be a red one, and they'd just be all mixed up, and they were equal numbers. So we'd have 4 students at a lab station, and they would just, without looking, pick out one and then keep the order as they picked them out. They kept them in line. Now, if there were equal numbers, theoretically, they would pick out a white one, and then the next time they should pick out a red one. But as we looked at the lines of these cylinders as we went along, they weren't red, white, red, white, red, white. Now, if we looked at only 4 of them, chances are you might get 4 red or 4 white. But then as you went around the table and you started to build up the data, we saw, and we started, and that's what we did, we took counts of this, that with very few, we didn't quite meet the 1 to 1, but as our data got larger and larger, then it did. So this is the law of large numbers, the law of averages. So as your amount of data increases, you move toward this, and that's what they're developing. So a fair coin was tossed 35 times. Well, how many times would you get ahead? Well, you think half of them should be that way. But you tossed and you got 3 tails. That's 0 times. But again, as you increase your data, if you're doing it in a fair, honest way, then you move toward the average, the mathematical average. And they give a little summation here comparing empirical and theoretical probabilities. So when we in biology did our Drosophila experiments with fruit flies, we would get physical results. That's our empirical. But then we compared it to the theoretical, and again, the larger the numbers, the closer it got to its theoretical probabilities, the larger the number of repetitions. And speaking about biology, here we get to Gregor Mendel, who is often considered the father of modern day genetics, because there was a lot of thought as to what results. They kept thinking that it was blending, but he said no, there were distinct things. So let's take a look at some of these. We're going to have pure red cross with pure white. And we have to define what we're going to use. If something is dominant, we usually use the capital letter. If something is recessive, we use the lowercase letter. And then we look at what we're going to get. And we could look at what we get here right from the chart. Now we used to make a little chart like so. So we'd say the parent that was red had two genes, both dominant, and the second parent, which was white, had two genes recessive for that trait. So this was, we call purebred, and then we made the cross. So now all of the offspring were red, but they were no longer pure red, they were hybrid. Now, when we cross the hybrid parents, and these were both red, because red is dominant, we got this combination. These gave you one purebred red. This would be a hybrid red. This would be a hybrid red. This would be a purebred white. And we would get some biology words. You don't need to know these. The phenotype and the genotype. Well, phenotype is the appearance of this. And the phenotype ratio here, we say, was 3:1. 3 red to 1 white. Now the genotype was the gene makeup. Were they the same? Well, this was one that was pure dominant. That was 1. We had 2 that were hybrid. And we had 1 that was recessive. So we say from a dihybrid cross, which is what is illustrated here, our ratio was 1 to 2 to 1. Now, when we were working with fruit flies, the Drosophila melanogaster, we would get a 3:1 phenotype ratio, but we couldn't really tell what was what. But again, there are certain kinds of experiments that we could do, and of course, this is where probability ties into biology, and we saw it right there. So, looking at the probabilities from this chart, and these are the results, how many would be red? Well, anything with the dominant would be red. Out of how many? Well, there would be 3 red out of a sample space of 4. And then how many would be white for letter B here? Well, there was 1 white out of a sample space of 4. So again, tying in a little bit of biology with our study here of probability. As we build vocabulary, we're now going to take a look at odds. Now, in gambling and horse racing and various things, they say, what are the odds? Well, odds are compared to probability, where probability we say this out of the possible outcomes here. 1 out of the total sample space. When we do odds, we usually say odds of winning as compared to losing. Or we can reverse it, losing compared to winning. That is, odds against rather than odds in favor, although you can switch them around. Now, generally speaking, the amount of odds for winning plus the amounts of losing is your sample space in probability. It's just a little different way of looking at it. And odds in favor, A to B, odds against, B to A, just switching them around. All right, let's take a look at example 8. So here Teresa has been promised 1 of 6 jobs, 3 of which would be an intern position. So what are her chances of getting an intern position? Well, since there are 3 intern positions, and there's a total of 6 possibilities, 3 would be intern, and 3 would not be intern. So we say the odds here are even, and often they use the expression a 50-50 chance. Now, if we looked at that in terms of probability, it would be 3 out of 6. But in odds, it's 3 out of 3. Well, remember, the total of this equals our sample space. So in example 9, the odds of winning a raffle, well, he purchased 12 tickets, and there were this many tickets sold. So again, this is a sample space. We're not looking for probability, we're looking for odds. So we subtract the 12 from the 104 and get 92. Now, the chance for losing would be 92 to 12, but the chance for winning would be 12 to 92, where again, the sum of these make up your sample space. And usually they don't leave it in these big numbers. They try to take out anything, both are divisible by 4. So here they're asking the odds against his winning. That's why they give the 92 first. Now here they give us a little summation of probability and odds. Generally, probability is what you are looking for out of the sample space. When we're doing odds, if A is what is winning or what you're looking for, it would be A, and then you would subtract the A from the B, as they show here, to show the odds. All right, let's go on. In example 10, they're converting from probability to odds. So keeping in mind what we just looked at, if the probability of rain is 30%, we put the 30 over 100, which simplifies 3 to 10. So if we subtract a 3 from the 10, we get 7. So the odds are 3 chances of it raining out of 7 chances or odds that it will not rain. So that's the odds, 3 to 7. So once again, we had our sample space as being, in this case, 10. The chance of the event you're looking for is 3. Subtract the 3 from the 10 to get the 7. So this is probability. These are odds. Now, if you want to say it the other way, the chance of having a sunny day would be 7. The chance of it raining would be 3. Odds against rain, sunny to rain. And again, you'll be practicing. I know it seems a little conflicting here at times. And for our last example, here we have a certain sweepstakes. Your odds of winning are this out of this. What would be your probability? Well, the event that you're looking for is 1. Now your sample space would be the sum of these. So you would add 1 to this and get 100,000. So this would be probability. This is odds. All right, and if we have time, we will take a look at some of these. And of course, you'll have your homework and your study plan.